Suppose I look at the registry of residents of my town and pick a person at random. What is the probability that this person is under 18 years of age? The answer is about 25%. Suppose now that I tell you that this person is married. Will you give the same answer? Of course not. The probability of being less than 18 years old is now much smaller. What happened here? We started with some initial probabilities that reflect what we know or believe about the world. But we then acquired some additional knowledge, some new evidence, for example, about this person's family situation. This new knowledge should cause our beliefs to change, and the original probabilities must be replaced by new probabilities that take into account the new information. These revised probabilities are what we call conditional probabilities, and this is the subject of this lecture. We will start with a formal definition of conditional probabilities, together with the motivation behind this particular definition. We will then proceed to develop three tools that rely on conditional probabilities, including the Bayes rule, which provides a systematic way for incorporating new evidence into a probability model. The three tools that we introduce in this lecture involve very simple and elementary mathematical formulas. Yet they encapsulate some very powerful ideas. It is not an exaggeration to say that much of this class will revolve around the repeated application of variations of these three tools to increasingly complicated situations. In particular, the Bayes rule is the foundation for the field of inference. It is a guide on how to process data and make inferences about unobserved quantities or phenomena. As such, it is a tool that is used all the time, all over science and engineering.
Conditional probabilities are probabilities associated with a revised model that takes into account some additional information about the outcome of a probabilistic experiment. The question is how to carry out this revision of our model. We will give a mathematical definition of conditional probabilities, but first let us motivate this definition by examining a simple concrete example. Consider a probability model with 12 equally likely possible outcomes, and so each one of them has probability equal to 1 over 12. We will focus on two particular events, event A and B, two subsets of the sample space. Event A has 5 elements, so its probability is 5 over 12, and event B has 6 elements, so it has probability 6 over 12. Suppose now that someone tells you that event B has occurred, but tells you nothing more about the outcome. How should the model change? First, those outcomes that are outside event B are no longer possible. So we can either eliminate them, as was done in this picture, or we might keep them in the picture but assign them 0 probability, so that they cannot occur. How about the outcomes inside the event B? So we are told that one of these has occurred. Now, these 6 outcomes inside the event B were equally likely in the original model, and there is no reason to change their relative probabilities, so they should remain equally likely in the revised model as well, so each one of them should have now probability 1 over 6, since there are 6 of them. And this is our revised model, the conditional probability law. 0 probability to outcomes outside B, and probability 1 over 6 to each one of the outcomes that is inside the event B. Let us write now this down mathematically. We will use this notation to describe the conditional probability of an event A, given that some other event B is known to have occurred. We read this expression as probability of A given B. So what are these conditional probabilities in our example? So in the new model, where these outcomes are equally likely, we note that event A can occur in two different ways. Each one of them has probability 1 over 6, so the probability of event A is 2 over 6, which is the same as 1/3. How about event B? Well, B consists of 6 possible outcomes, each with probability 1 over 6, so event B in this revised model should have probability equal to 1. Of course, this is just saying the obvious. Given that we already know that B has occurred, the probability that B occurs in this new model should be equal to 1. How about now if the sample space does not consist of equally likely outcomes, but instead we're given the probabilities of different pieces of the sample space, as in this example. Notice here that the probabilities are consistent with what was used in the original example. So this part of A that lies outside B has probability 3 over 12. But in this case, I'm not telling you how that probability is made up. I'm not telling you that it consists of 3 equally likely outcomes. All I'm telling you is that the collective probability in this region is 3 over 12. The total probability of A is again 5 over 12 as before. The total probability of B is 2 plus 4 equals 6/12, exactly as before. So it's a sort of similar situation as before. How should we revise our probabilities and construct conditional probabilities once we are told that event B has occurred? First, this relation should remain true. Once we are told that B has occurred, then B is certain to occur, so it should have conditional probability equal to 1. How about the conditional probability of A given that B has occurred? Well, we can reason as follows. In the original model, and if we just look inside event B, those outcomes that make event A to happen had a collective probability which was 1/3 of the total probability assigned to B. So out of the overall probability assigned to B, 1/3 of that probability corresponds to outcomes in which event A is happening. So therefore, if I tell you that B has occurred, I should assign probability equal to 1/3 that event A is also going to happen. So that, given that B happened, the conditional probability of A given B should be equal to 1/3. By now, we should be satisfied that this approach is a reasonable way of constructing conditional probabilities, but now let us translate our reasoning into a formula. So we wish to come up with a formula that gives us the conditional probability of an event given another event. The particular formula that captures our way of thinking, as motivated before, is the following. Out of the total probability assigned to B, which is this, we ask the question, which fraction of that probability is assigned to outcomes under which event A also happens? So we are living inside event B, but within that event, we look at those outcomes for which event A also happens. So this is the intersection of A and B. And we ask, out of the total probability of B, what fraction of that probability is allocated to that intersection of A with B. So this formula, this definition, captures our intuition of what we did before to construct conditional probabilities in our particular example. Let us check that the definition indeed does what it's supposed to do. In this example, the probability of the intersection was 2 over 12, and the total probability of B was 6 over 12. Which gives us 1/3, which is the answer that we had gotten intuitively a little earlier. At this point, let me also make a comment that this definition of conditional probabilities makes sense only if we do not attempt to divide by 0. That is only if the event B on which we are conditioning has positive probability. If an event B has 0 probability, then conditional probabilities given B will be left undefined. And one final comment. This is a definition, it's not a theorem. What does that mean? It means that there is no question whether this equality is correct or not. It's just a definition. There's no issue of correctness. The earlier argument that we gave was just a motivation of the definition. We tried to figure out what the definition should be if we want to have a certain intuitive and meaningful interpretation of the conditional probabilities. Let us now continue with a simple example. This is a simple example where we want to just apply the formula for conditional probabilities and see what we get. The example involves a four-sided die, if you can imagine such an object, which we roll twice and we record the first roll and the second roll, so there are 16 possible outcomes. We assume, to keep things simple, that each one of those 16 possible outcomes, each one of them has the same probability, so each outcome has probability 1 over 16. Let us consider now a particular event B on which we are going to condition. This is the event under which the smaller of the two die rolls is equal to 2, which means that one of the dice must have resulted in 2 and the other die has resulted in something which is 2 or larger. So this can happen in multiple ways, and here are the different ways that it can happen. So a 2-2 or a 2-3, a 2-4, then a 3-2 and a 4-2. All these are outcomes in which one of the dice has a value equal to 2 and the other die is at least as large. So we condition on this event. This results in a conditional model where each one of those 5 outcomes are equally likely since they used to be equally likely in the original model. Now let us look at this quantity, the maximum of the two die rolls, that is the largest of the results, and let us try to calculate the following quantity, the conditional probability that the maximum is equal to 1 given that the minimum is equal to 2. So this is the conditional probability of this particular outcome. Well, this particular outcome cannot happen. If I tell you that the smaller number is 2, then the larger number cannot be equal to 1. So this outcome is impossible, and therefore this conditional probability is equal to 0. Let's do something a little more interesting. Let us now look at the conditional probability that the maximum is equal to 3 given the information that event B has occurred. It's best to draw a picture and see what that event corresponds to. M is equal to 3, the maximum is equal to 3 if one of the dice resulted in a 3 and the other die resulting in something that's 3 or less. So this event here corresponds to the blue region in this diagram. Now let us try to calculate the conditional probability by just following the definition. The conditional probability of one event given another is the probability that both of the two events occur divided by the probability of the conditioning event. That is, out of the total probability in the conditioning event, we ask what fraction of that probability is assigned to outcomes in which the event of interest is also happening. So, what is this event? The maximum is equal to 3, which is the blue event, and simultaneously the red event is happening. These two events intersect only in two places. This is the intersection of the two events, and the probability of that intersection is 2 out of 16. Since there's 16 outcomes and that event happens only with two particular outcomes. So this gives us 2 over 16 in the numerator. How about the denominator? Event B consists of a total of 5 possible outcomes. Each one has probability 1/16. So this is 5 over 16. So the final answer is 2 over 5. We could have gotten that same answer in a simple and perhaps more intuitive way. In the original model, all outcomes were equally likely. Therefore, in the conditional model, the 5 outcomes that belong to B should also be equally likely. Out of those 5, there's 2 of them that make the event of interest to occur. So given that we live in B, there's 2 ways out of 5 that the event of interest will materialize. So the event of interest has conditional probability equals to 2/5. I now want to emphasize an important point. Conditional probabilities are just the same as ordinary probabilities applied to a different situation. They do not taste or smell or behave any different than ordinary probabilities. What do I mean by that? I mean that they satisfy the usual probability axioms. For example, ordinary probabilities must also be non-negative. Is this true for conditional probabilities? Of course it is true, because conditional probabilities are defined as a ratio of two probabilities. Probabilities are non-negative, so the ratio will also be non-negative, of course, as long as it is well defined. And here we need to remember that we only talk about conditional probabilities when we condition on an event that itself has positive probability. How about another axiom? What is the probability of the entire sample space given the event B? Let's check it out. By definition, the conditional probability is the probability of the intersection of the two events involved divided by the probability of the conditioning event. Now, what is the intersection of omega with B? B is a subset of omega, so when we intersect the two sets, we're left just with B itself. So the numerator becomes the probability of B. We're dividing by the probability of B, and so the answer is equal to 1. So indeed, the sample space has unit probability even under the conditional model. Now, remember that when we condition on an event B, we could still work with the original sample space. However, possible outcomes that do not belong to B are considered impossible, so we might as well think of B itself as being our sample space. If we proceed like that and think now of B as being our new sample space, what is the probability of this new sample space in the conditional model? Let's apply the definition once more. It's the probability of the intersection of the two events involved, B intersection B, divided by the probability of the conditioning event. What is the numerator? The intersection of B with itself is just B, so the numerator is the probability of B. We're dividing by the probability of B, so the answer is again 1. Finally, we need to check the additivity axiom. Recall what the additivity axiom says. If we have two events, two subsets of the sample space that are disjoint, then the probability of their union is equal to the sum of their individual probabilities. Is this going to be the case if we now condition on a certain event? What we want to prove is the following statement. If we take two events that are disjoint, they have empty intersection, then the probability of the union is the sum of their individual probabilities, but where now the probabilities that we're employing are the conditional probabilities given the event B. So let us verify whether this relation, this fact, is correct or not. Let us take this quantity and use the definition to write it out. By definition, this conditional probability is the probability of the intersection of the first event of interest, the one that appears on this side of the conditioning, intersection with the event on which we are conditioning. And then we divide by the probability of the conditioning event B. Now let's look at this quantity. What is it? We're taking the union of A with C and then intersect it with B. This union consists of these two base pieces. When we intersect with B, what is left is these two pieces here. So A union C intersected with B is the union of two pieces. One piece is A intersection B, this piece here, and another piece which is C intersection B. This is the second piece here. So here we basically used a set theoretic identity, and now we divide by the same numerator as before. And now let us continue. Here's an interesting observation. The events A and C are disjoint. The piece of A that also belongs in B, therefore, is disjoint from the piece of C that also belongs to B. Therefore, this set here and that set here are disjoint. Since they are disjoint, the probability of their union has to be equal to the sum of their individual probabilities. So here we are using the additivity axiom on the original probabilities to break this probability up into two pieces. And now we observe that here we have the ratio of an intersection by the probability of B. This is just the conditional probability of A given B using the definition of conditional probabilities. And the second part is the conditional probability of C given B, where again we're using the definition of conditional probabilities. So we have indeed checked that this additivity property is true for the case of conditional probabilities when we consider two disjoint events. Now we could repeat the same derivation and verify that it is also true for the case of a disjoint union or of finitely many events, or even for countably many disjoint events. So we do have finite and countable additivity. We're not proving it, but the argument is exactly the same as for the case of two events. So conditional probabilities do satisfy all of the standard axioms of probability theory. So conditional probabilities are just like ordinary probabilities. This actually has a very important implication. Since conditional probabilities satisfy all of the probability axioms, any formula or theorem that we ever derive for ordinary probabilities will remain true for conditional probabilities as well. Let us now examine what conditional probabilities are good for. We have already discussed that they are used to revise a model when we get new information. But there is another way in which they arise. We can use conditional probabilities to build a multi-stage model of a probabilistic experiment. We will illustrate this through an example involving the detection of an object up in the sky by a radar. We will keep our example very simple. On the other hand, it turns out to have all the basic elements of a real-world model. So, we are looking up in the sky, and either there's an airplane flying up there or not. Let us call event A the event that an airplane is indeed flying up there. And we have two possibilities. Either event A occurs or the complement of A occurs, in which case nothing is flying up there. We also, at this point, we can also assign some probabilities to these two possibilities. Let us say that through prior experience perhaps or some other knowledge, we know that the probability that something is indeed flying up there is 5%, and with probability 95%, nothing is flying. Now we also have a radar that looks up there, and there are two things that can happen. Either something registers on the radar screen or nothing registers. Of course, if it's a good radar, probably event B will tend to go together with event A, but it's also possible that the radar will make some mistakes. And so we have various possibilities. If there's a plane up there, it's possible that the radar will detect it, in which case event B will also happen, but it's also conceivable that the radar will not detect it, in which case we have a so-called miss, and so a plane is flying up there, but the radar missed it, did not detect it. Another possibility is that nothing is flying up there, but the radar does detect something, and this is a situation that's called a false alarm. Finally, there's the possibility that nothing is flying up there and the radar did not see anything either. Now let us focus on this particular situation. Suppose that event A has occurred. So we are living inside this particular universe. In this universe, there are two possibilities, and we can assign probabilities to these two possibilities. So let's say that if something is flying up there, our radar will find it with probability 99%, but will also miss it with probability 1%. What's the meaning of this number, 99%? Well, this is a probability that applies to a situation where an airplane is up there. So it is really a conditional probability. It's the conditional probability that we will detect something, the radar will detect the plane, given that the plane is already flying up there. And similarly, this 1% can be thought of as the conditional probability that the complement of B occurs, so the radar doesn't see anything, given that there is a plane up in the sky. We can assign similar probabilities to under the other scenario. If there is no plane, there is a probability that there will be a false alarm, and there is a probability that the radar will not see anything. Those four numbers here are, in essence, the specs of our radar. They describe how the radar behaves in a world in which an airplane has been placed in the sky, and some other numbers that describe how the radar behaves in a world where nothing is flying up in the sky. So we have described various probabilistic properties of our model, but is it a complete model? Can we calculate anything that we might wish to calculate? Let us look at this question. Can we calculate the probability that both A and B occur? It's this particular scenario here. How can we calculate it? Well, let us remember the definition of conditional probabilities. The conditional probability of an event given another event is the probability of their intersection divided by the probability of the conditioning event. But this doesn't quite help us because if we try to calculate the numerator, we do not have the value of the probability of A given B. We have the value of the probability of B given A. What can we do? Well, we notice that we can use this definition of conditional probabilities, but use it in the reverse direction, interchanging the roles of A and B. If we interchange the roles of A and B, our definition leads to the following expression. The conditional probability of B given A is the probability that both events occur divided by the probability, again, of the conditioning event. Therefore, the probability that A and B occur is equal to the probability that A occurs times the conditional probability that B occurs given that A occurred. And in our example, this is 0.05 times the conditional probability that B occurs, which is 0.99. So we can calculate the probability of this particular event by multiplying probabilities and conditional probabilities along the path in this tree diagram that leads us here. And we can do the same for any other leaf in this diagram. So for example, the probability that this happens is going to be the probability of this event times the conditional probability of B complement given that A complement has occurred. How about a different question? What is the probability, the total probability that the radar sees something? Let us try to identify this event. The radar can see something under two scenarios. There's the scenario where there is a plane up in the sky and the radar sees it. And there's another scenario where nothing is up in the sky, but the radar thinks that it sees something. So these two possibilities together make up the event B. And so to calculate the probability of B, we need to add the probabilities of these two events. For the first event, we already calculated it. It's 0.05 times 0.99. For the second possibility, we need to do a similar calculation. The probability that this occurs is equal to 0.95 times the conditional probability of B occurring under the scenario where A complement has occurred. And this is 0.1. If we add those two numbers together, the answer turns out to be 0.1445. Finally, a last question, which is perhaps the most interesting one. Suppose that the radar registered something. What is the probability that there is an airplane out there? How do we do this calculation? Well, we can start from the definition of the conditional probability of A given B, and note that we already have in our hands both the numerator and the denominator. So the numerator is this number 0.05 times 0.99, and the denominator is 0.1445, and we can use our calculators to see that the answer is approximately 0.34. So there is a 34% probability that an airplane is there, given that the radar has seen or thinks that it sees something. So the numerical value of this answer is somewhat interesting because it's pretty small. Even though we have a very good radar that tells us the right thing 99% of the time under one scenario and 90% under the other scenario, despite that, given that the radar has seen something, this is not really convincing or compelling evidence that there is an airplane up there. The probability that there is an airplane up there is only 34% in a situation where the radar thinks that it has seen something. So in the next few segments, we are going to revisit these three calculations and see how they can generalize. In fact, a large part of what is to happen in the remainder of this class will be elaboration on these three ideas. There are three types of calculations that will show up over and over, of course in more complicated forms, but the basic ideas are essentially captured in this simple example. As promised, we will now start developing generalizations of the different calculations that we carried out in the context of the radar example. The first kind of calculation that we carried out goes under the name of the multiplication rule, and it goes as follows. Our starting point is the definition of conditional probabilities. The conditional probability of A given another event B is the probability that both events have occurred divided by the probability of the conditioning event. We now take the denominator term and send it to the other side of this equality to obtain this relation, which we can interpret as follows. The probability that two events occur is equal to the probability that a first event occurs, event B in this case, times the conditional probability that the second event, event A, occurs, given that event B has occurred. Now, out of the two events A and B, we are of course free to choose which one we call the first event and which one we call the second event, so the probability of the two events happening is also equal to an expression of this form, the probability that A occurs times the conditional probability that B occurs, given that A has occurred. We used this formula in the context of a tree diagram, and we used it to calculate the probability of a leaf of this tree by multiplying the probability of taking this branch, the probability that A occurs, times the conditional probability of taking this branch, the probability that event B also occurs, given that event A has occurred. How do we generalize this calculation? Consider a situation in which the experiment has an additional third stage that has to do with another event C that may or may not occur. For example, if we have arrived here, A and B have both occurred, and then C also occurs, then we reach this particular leaf of the tree. Or there could be other scenarios. For example, it could be the case that A did not occur, then event B occurred, and finally event C did not occur, in which case we end up at this particular leaf. What is the probability of this scenario happening? Let us try to do a calculation similar to the one that we used for the case of two events. However, we need to deal here with three events. What should we do? Well, we look at the intersection of these three events and think of it as the intersection of a composite event, A complement intersection B, then intersected with the event C complement. Clearly, you can form the intersection of three events by first taking the intersection of two of them and then intersecting with the third. After we group things this way, we are dealing with the probability of two events happening, this composite event and this ordinary event, and the probability of two events happening is equal to the probability that the first event happens and then the probability that the second event happens, given that the first one has happened. Can we simplify this even further? Yes, the first term is the probability of two events happening, so it can be simplified further as the probability that A complement occurs times the conditional probability that B occurs, given that A complement has occurred. And then we carry over the last term exactly the way it is. The conclusion is that we can calculate the probability of this leaf by multiplying the probability of the first branch times the conditional probability of the second branch, given that the first branch was taken, and then finally multiply with the probability of the third branch, which is the probability that C complement occurs, given that A complement and B have already occurred. In other words, we can calculate the probability of a leaf by just multiplying the probabilities of the different branches involved and where we use conditional probabilities for the intermediate branches. At this point, you can use your imagination to see that such a formula should also be valid for the case of more than 3 events. The probability that a bunch of events all occur should be the probability of the first event times a number of factors, each corresponding to a branch in a tree of this kind. In particular, the probability that events A1, A2, up to AN all occur is going to be the probability that the first event occurs times a product of conditional probabilities that the ith event occurs, given that all the previous events have already occurred. And we obtain a term of this kind for every event AI after the first one, so this product ranges from 2 up to n. And this is the most general version of the multiplication rule and allows you to calculate the probability of several events happening by multiplying probabilities and conditional probabilities. Let us now revisit the second calculation that we carried out in the context of our earlier example. In that example, we calculated the total probability of an event that can occur under different scenarios, and it involves the powerful idea of divide and conquer, where we break up complex situations into simpler pieces. Here is what is involved. We have our sample space, and our sample space is partitioned into a number of subsets or events. In this picture, we take that number to be 3, so we have a partition into 3 possible scenarios. It is a partition, which means that these events cover the entire sample space, and they are disjoint from each other. For each one of the scenarios, we're given their probabilities. If you prefer, you can also draw this situation in terms of a tree. There are 3 different scenarios that can happen. We're interested in a particular event B. That event B can happen in 3 different ways. It can happen under scenario 1, under scenario 2, or under scenario 3, and this corresponds to these particular sub-events. So for example, this is the event where scenario A1 happens, and then event B happens as well. In terms of a tree diagram, the picture becomes as follows. If scenario A1 materializes, event B may occur, or event B might not occur. Finally, we are given conditional probabilities that event B will materialize under each one of the different possible scenarios. Under those circumstances, can we calculate the probability of event B? Of course we can, and here's how we do it. First, we realize that event B consists of a number of disjoint pieces. One piece is when event B occurs together with event A1. Another piece is when event B occurs together with A2. Another piece is when event B occurs together with A3. These 3 sets are disjoint from each other, as we see in this picture, and together they form the event B. Therefore, the probability of B is going to be, by the additivity axiom of probabilities, equal to the sum of the probabilities of these sub-events. Furthermore, for each one of these sub-events, we can use the multiplication rule and write their probabilities as follows. The probability that B and A1 both occur is the probability that scenario 1 materializes times the conditional probability that B occurs given that A1 occurred. And then we're going to have similar terms under the second scenario and a similar term under the third scenario. So putting everything together, we have derived at a formula of this form. The total probability of event B is the sum of the probabilities of the different ways that B may occur. that is B occurring under the different scenarios, and those particular probabilities are the product of the probability of the scenario times the conditional probability of B given that scenario. Now note that the sum of the probabilities of the different scenarios is of course equal to 1, and this is because the scenarios form a partition of our sample space. So if we look at this formula here, we realize that it is a weighted average of the conditional probabilities of event B. It's a weighted average of the conditional probabilities where these probabilities of the individual scenarios are the weights. In words, the probability that an event occurs is a weighted average of the probability that it has under each possible scenario, where the weights are the probabilities of the different scenarios. One final comment. Our derivation was for the case of 3 events, but you can certainly see that the same derivation would go through if we had any finite number of events. But even more, if we had a partition of our sample space into an infinite sequence of events, the same derivation would still go through, except that in this place in the derivation, instead of using the ordinary additivity axiom, we would have to use the countable additivity axiom. But other than that, all the steps would be the same, and we would end up with the same formula, except that now this would be an infinite sum over the infinite set of scenarios. We now come to the third and final kind of calculation out of the calculations that we carried out in our earlier example. The setting is exactly the same as in our discussion of the total probability theorem. We have a sample space which is partitioned into a number of disjoint subsets or events which we think of as scenarios. We are given the probability of each scenario, and we think of these probabilities as being some kind of initial beliefs. They capture how likely we believe each scenario to be. Now, under each scenario, we also have the probability that an event of interest, event B, will occur. Then the probabilistic experiment is carried out, and perhaps we observe that event B did indeed occur. Once that happens, maybe this should cause us to revise our beliefs about the likelihood of the different scenarios. Having observed that B occurred, perhaps certain scenarios are more likely than others. How do we revise our beliefs? By calculating conditional probabilities. And how do we calculate conditional probabilities? We start from the definition of conditional probabilities. The probability of one event given another is the probability that both events occur divided by the probability of the conditioning event. How do we continue? Well, we simply realize that the numerator is what we can calculate using the multiplication rule, and the denominator is exactly what we calculate using the total probability theorem. So we have everything we need to calculate those revised beliefs or conditional probabilities, and this is all there is in the Bayes rule. It is actually a very simple calculation. It's a very simple calculation, however it is a quite important one. Its history goes way back. In the middle of the 18th century, a Presbyterian minister, Thomas Bayes, worked it out. It was published a few years after his death, and it was quickly recognized for its significance. It's a systematic way for incorporating new evidence. It's a systematic way for learning from experience. And it forms the foundation of a major branch of mathematics, so-called Bayesian inference, which we will study in some detail later in this course. The general idea is that we start with a probabilistic model, which involves a number of possible scenarios, and we have some initial beliefs on the likelihood of each possible scenario. There's also some particular event that may occur under each scenario, and we know how likely it is to occur under each scenario. This is our model of the situation. Under each particular situation, the model tells us how likely event B is to occur. If we actually observe that B occurred, then we use that information to draw conclusions about the possible causes of B, or conclusions about the more likely or less likely scenarios that may have caused this event to occur. And that's what inference is. Having observed B, we make inferences as to how likely a particular scenario AI is going to be, and that likelihood is captured by these conditional probabilities of AI given the event B. So that's what the Bayes rule is doing. Starting from conditional probabilities going in one direction, it allows us to calculate conditional probabilities going in the opposite direction. It allows us to revise the probabilities of the different scenarios, taking into account the new information, and that's exactly what inference is all about, as we're going to see later in this class.